Electron configurations are kind of the conglomeration of everything that we've just learned in quantum mechanics, how it's applied in general chemistry. Okay? If I look at hydrogen, I know that hydrogen has one total electron. Okay? Now we have to give a sort of condensed configuration of how many of these electrons there are and in what quantum states they're going to be in. Okay? So I know we start with the lowest number, and the lowest number we have is 1, and that's n, right? So we know that the S shape is the only shape that's there, and that's when L is equal to 0. Okay? And we look at the magnetic spin, and magnetic spin is not really accounted for in electronic configuration. It just tells us how many orbitals there are. And I know that there's just one orbital of S. Okay? And how many electrons are in there? It's either 1/2 or minus 1/2. That's one electron. So the electronic configuration of hydrogen is of this form. Okay? It's of n, principal quantum number, all right? And then it states L, and in L I say that it's the S, P, D, or F block, all right? And then the magnetic spin quantum number is up there, okay? Now the magnetic spin quantum number, notice that we have 1 here, it's not 1/2. It just tells us how many electrons are in each one of the orbitals. Let's keep going further and see how this is applied in chemistry. Right? So if I go to helium, the total number of electrons I have is 2. So I still have 1, okay? That's the principal quantum level. And then S, okay? And I've got to put 2 electrons in there. So now at that point, that's full, okay? Because I've got 2 electrons in the S orbital. There's only one direction in the S, so the maximum number of electrons I can put in there is 2. Let's jump up. Let's go to lithium. All right, lithium has 3 electrons. I cannot do this. I cannot go 1s3. All right, that 3 is incorrect because I can only have 2 electrons in there. So if I've got 2 electrons here, I've got to account for that third electron somewhere. So I have to go up one more level. And the reason I have to go up is that I can't have P, D, or F when the principal quantum number is 2. Remember, L is equal to 0. It's the only value that we've got. So now I've got 2, and I always start with S again. So that's 2s1. Okay? I can represent these things using additional boxes. And sometimes it's easier to see when I use these additional boxes. So let's look at hydrogen. And hydrogen, I know, has a 1s box. And there's 1 electron in there. Okay? And I generally draw these pointing upwards first. You can point it up, point it down. It doesn't matter. When I go to helium, there's my 1s, and now I've got 2 electrons in there. If I draw it like that, that is not correct. The spins have to be opposite. If I put them both pointing upwards, that both implies a plus 1/2 magnetic spin state. That can't work. Okay, remember, that's one of our principles, Pauli exclusion principle. That's right, you can't have 2 things with the same quantum map, essentially. All right, so I have to draw this other arrow so that it's pointing downwards. Okay. Now I go to lithium. Lithium is 1s. There are 2 electrons there. I can't put a third electron in that box, so I have to go up, and I go to my 2s box. Right? And it can be either up or down because there's only 1 electron there. If I go to beryllium, okay, beryllium has 4 electrons. It's right after lithium. My arrow would be pointing down. And what would my electron configuration be? My electron configuration for beryllium, you're right, would be a 2 there. Okay? Let's keep going. Let's go up a little bit, and let's go to carbon. Carbon has 6 electrons total. Okay? So my electronic configuration is 1s2. There's 2 electrons accounted for. 2s2. And now, what am I going to go to at this point? I filled up S. So at this point, what I've got for S is N is equal to 2, L is equal to 0, and my M is equal to 0 at this point. Right? So that's just the 2 electrons there. Is L equal to 1 legal for this quantum state? Yes, it is. Right? And that's our P shell. It's our first node encounter. So 2P, and I've got 2 electrons here. 2, 4, 6. So I've got 6 total electrons. So this is N is equal to 2. L is equal to 1 here. My M can be -1, 0, or +1. And I can put 2 electrons into each one of those little boxes. Okay? So if I draw this in box shape, so you can see it a little bit better, I have the same thing that I have with lithium and beryllium. There's 1s, here's 2s, up, down, up, down. Now when I go to 2p, my boxes have expanded a little bit. Okay, one of them is mx, one is my, and one is mz. If I looked at this from a quantum number state, this would be -1, 0, or +1. Or +1, 0, -1, or 0, +1, -1. However you want to organize it. It doesn't matter so long as all are represented, right? Okay, so where are these electrons going to go now? Okay, 1 electron here, 1 electron there. I don't pair them up, okay? I don't pair them up because that's Hund's rule, right? Okay, and we're following the Aufbau principle where we fill them up from lowest energy to highest energy first. Now some people are looking at this and they're thinking, well, Dr. Wayne, 2s and 2p both have quantum number base state, or principal quantum number 2, okay? So why do I pair these electrons and not move this electron over? And do this. Can I do that? And the answer I give you is maybe. It depends on the state of carbon. Right? You're not pairing things up at this point, that's fine. But 2s and 2p, the energies are a little bit different. If I look at an energy diagram, right, my 2s would be here, and my 2p would be just above the 2s. So it's a little bit higher in energy. How much energy do you get when you pair electrons? Where is that going to push the 2s state? Right? Yeah, I'll give you one of those. The indefinitive, I'm an organic chemist. I don't really know a lot about quantum states at this particular time. Right? These things, these levels, they change. If you start pairing things up, obviously you put 2 electrons in, it's going to boost the energy. Okay, and what's that going to do here? This is kind of a paper example. And the reason I give you a paper example is that you don't find carbon in this state. Carbon does something a little bit fun, all right? Because it's organic chemistry, so obviously it's going to be fun. So it does something a little bit fun called hybridization. So these types of things, they're more of an academic exercise. And if you want to do this, that's fine. If you wanted to put it in the other direction, that's fine with me, okay? In my class, I don't really care whichever way you do this, so long as you follow all the principles, right? Have I violated any principles here? Well, I've got 2 electrons here. That's Hund's rule. Look at Hund's rule. Am I okay with Hund's rule? Well, 2s is lower in energy than 2p. If you explain it to me that way, that's fine. Put the other electron over there and just say, well, I'm not pairing electrons up, I'm following Hund's rule. That's fine with me as well, okay? Because both Aufbau and Hund apply in this case. It depends on the energy that you've got here. Okay, a long explanation for I don't care what you put here so long as you do it correctly. Either pair them up or over there. Make sure you've got 4 electrons. Okay? So let's go a little bit more, right? And I'm going to go to oxygen. Oxygen at this point has 8 total electrons. My electronic configuration is 1s2, 2s2, 2p4 for my 8 electrons. When I look at my electronic configuration, in the boxes, I've got 1s, 1s is right here. Here's 2s and 2p, okay? Electron up, electron down, electron up, electron down. All right, Now what am I going to do with those other 4 electrons? Do I pair them like this? Or is that bad? Have I done something naughty? It's not good. No. Why? Because it violates somebody's rule. Okay, Hund's rule, right? Don't pair the electrons unless you have to. So split it up. Okay? And one thing that we like to see is all the electrons pointing in the same direction in the state. If they point opposite directions, you get a different type of quantum state. So put them all pointing in the right direction. Okay? So notice what I did here. When I moved that electron over, that's just an artifact of me being well trained. All the electrons are pointing in the same direction. If they point the opposite direction, the spins don't align. When that happens, you get some weirdness. You get some energy changes. Okay, so make sure everything is pointing in the right direction, unless it's paired, because then you got 1 and 1, right? All right. So, does it matter where I put this other electron? The answer is no, so long as you pair the electron. If it has to go somewhere, make sure you put it in there. Okay? Okay. Now I'm going to jump up. I'm going to go to sulfur. All right, sulfur at this point is 16. The electronic configuration, 1s2, 2s2, 2p6. At this point I have 10 electrons total. What do you think comes next? 3, good. All right. What orbital? S, good. All right, and then I'm going to put the number that I need here. And that's 8, right? Does that make sense? Have I done something bad? The answer is yes. I've done something horrible. Okay? What have I done? Too many electrons in the S state. Remember, S has always got 2 electrons in it. So don't do that. S is always 2 electrons. So what's next after this? What's lower in energy, P or D? D has 2 nodes, P has 1 node. So we go to P first, Aufbau's principle. You start filling the P first. So 3P, and then I'm going to put 4 electrons there. Okay? And to show you a quick box diagram of how these things work, I'm not going to write in 1s here, because we know what that is. Here's 2s, electron up, electron down. 2p, 1, 2. Okay. And let's go to 3s. Alright, and then we'll go to 3p, which is the next level. Alright, and it's sure enough, it looks exactly like oxygen. If you look at the periodic table, they're right next to each other. It's a hint. They have similar electronic configurations. Alright, I want to point something else here. I've drawn in helium up here. And here on sulfur, I'm going to draw this. This electronic configuration is neon. Alright? And if I put 2 more electrons in here, this is argon. And at this point, when I put those other 2 electrons in, I've got that full electron configuration. Alright? When my boxes are full, they're special. It means that they don't like to react. So even something as simple as beryllium, okay, when I put those 2 electrons in there, beryllium kind of stays on its own little state and says, I've got a full shell, I don't like to react. Okay? Matter of fact, if you find beryllium in nature, beryllium doesn't form diatomic or multiatomic elements. Instead, we find beryllium is always monoatomic. The reason being is that it doesn't like to bond with anything, because its shell is full. Alright? That's what we call the bond order 0. You have to learn about that later. Okay? So, this is the basics of electronic configuration. I am going to go to the next part, or next video part. We'll do some examples of this, and then I will show you how this relates to the periodic table.